Okay. So, hi everyone. So, good afternoon. Good afternoon all. So, we are dealing with the subject electromagnetics, and the topic name is electrostatic potential energy. So, now we are dealing with electrostatic potential energy, right? Okay. So, I will just revise whatever I have done in the previous session here. Okay. Okay. See here, I have considered some charge distribution. So, I have considered some charge distribution. So, whenever I consider some charge distribution, it is going to set up what here? It is going to set up some electric field in its vicinity. Yes or no? So, whenever I consider some charge distribution, it is going to set up some electric field in its vicinity. Understood? Okay. Okay, yeah. So, now whatever the field it is set up here, whatever the field that is set up by this charge distribution, what that field is going to do? So, that field is going to exert the forces on other charges. That means, if you try to bring any other charges into this field region, if you try to bring any other charges into this field region, then this field is going to exert the force on that charges. Understood? Okay. So, if the charge distribution and the charge that I am taking into this field, if both are of same polarity, then this charge is going to experience a repulsive force. Yes or no? So, the charge is going to experience a repulsive force. Now, if I try to bring a charge which is of opposite polarity here, opposite polarity to the charge distribution, then that charge is going to experience a attractive force. Understood? So, finally the thing is, whenever you are having some charge distribution, it is going to set up some electric field in its vicinity, and this field is going to exert the forces on other charges. So, if the other charge is of same polarity as this charge distribution, then that charge is going to experience a repulsive force. If the charge distribution and the charge which you are trying to take into this field is of opposite polarity, then it is going to experience a attractive force. Understood? Okay. So, this field is going to exert the forces on other charge carriers here. Understood? So, this is what you have to understand. Now, yesterday I have told that if you move an infinite distance, from this charge distribution, so you have moved to an infinite distance from that charge distribution. So, from infinity distance, you try to take a charge, q, which is of same polarity as this charge distribution. Let us assume this charge distribution is positive, then this charge q is also what? Q is also, I am considering it as what? Positive. Understood? Okay. So, I am going to infinity here. So, from infinity distance, I am trying to bring this charge from infinity to this distance r. So, let us say the distance from here to here is r. Understood? Okay. So, I am trying to bring this charge from infinity to what? From infinity to r. So, whenever I try to bring this charge from infinity to r, what will happen here? So, whenever I am moving this charge here, into this field region, so what this field is going to do? So, this field is going to exert a force on this charge. Yes or no? So, against that force, if I try to move this charge, if I want to move this charge, then I have to do what? I have to do some work. Yes or no? So, I am applying a force on this charge and trying to move against this field force, Yes or no? So, whenever I am moving this charge against the field force, I have to apply a force and I am trying to move this charge. That means you are having both force as well as what? As well as displacement. That means you have to do some work in order to move the charge from infinity to this location. So, whatever the work you are doing here, that will be stored as what? That will be stored as potential energy. Understood? Okay. So, here, while moving this charge from infinity to r, we have made some assumptions and approximations. So, what are those assumptions and approximations here? So, here at infinity, I have considered the charge initially is at what? It is at rest. I have assumed that the charge is at rest. That means the velocity of the charge is equal to what? The velocity of the charge is equal to 0. Understood? Okay. So now what is the assumption I am making here is I am going to move this charge. I am going to move this charge from infinity to this location such that there should not be any change in velocity. There should not be any change in velocity. So that means what here? Here the velocity is equal to 0 means here the velocity is equal to 0. Now I want to move this charge from infinity to this point without changing its velocity. So what I will do here is, since here velocity is 0, so what I will do here is I will slowly move this charge here. I will move this charge very slowly such that I can consider the velocity of this charge is approximately equal to what? Approximately equal to 0. It is slightly greater than 0. That's it. Understood? But it is I can approximate that velocity is equal to what? Is equal to 0. So what is the assumption we are making? We are going to move this charge. We are going to move this charge from infinity to this point such that its velocity should not change. So already its velocity at infinity is equal to what? Is equal to 0. So I should not change this velocity. That means I have to move this charge very slowly such that still I can approximate the velocity is equal to 0. Understood? So these are the assumptions and approximations we are making. So that means throughout this process, so I am trying to bring this charge into this field region. So while bringing this charge into this field region, I have to apply a force. In this direction. Yes or no? So I have to apply a force in this direction, and the electric force is acting in this direction. Electrical field force is acting in this direction. So against this field force, I have to apply external force in this direction. Understood? Okay. Okay. So here I am assuming throughout this process velocity is approximately equal to 0. So that means I am assuming that there is no change in velocity. I am assuming that there is no change in velocity. So if there is no change in velocity, I can say that the change in kinetic energy is also equal to what? The change in kinetic energy is also equal to 0. Understood? So what happens if there is no change in velocity? Then I can consider it as the change in kinetic energy is equal to what? Is equal to 0. So what do you mean by this? See here. See on any object here, if there acts any net force, that means if net force on any object is not equal to 0, then that object is going to experience what? Acceleration or not. See, we know that F net, if any force acts on object, then it is going to equal to what? It is going to equal to m into a. Yes or no? So if net force is not equal to 0, then that object is going to have what? Then that object is going to accelerate. Acceleration means what here? Acceleration means its velocity is going to change. Understood? So acceleration means I can write it as what? M into dv by dt. Yes or no? So if the velocity is changing with respect to time, okay, then only we can have acceleration. Understood? Okay, but here what is the assumption we are making? The velocity is approximately equal to 0, and we are assuming that there will be no change in velocity, and hence the change in kinetic energy is also equal to 0. So in this case we are assuming that there is no change in velocity. So that means this dv by dt will go to what? Will go to 0. So that means the net force on the charge must be equal to what? The net force on the charge must be equal to 0. That means whatever the forces that are acting on that charge here, so the total net forces must be equal to what? Must be equal to 0. Why here? Because the charge is not accelerating. That means the velocity of the charge is not changing. So that is the assumption we are making or not? Yes or no? Okay. Okay, so if the net force on the charge is not equal to 0 means here on this charge, what are the forces that are acting here? So one is electrical field force that is acting in this direction, and another one is what? External force that is acting in this direction. Yes or no? So I am moving this charge. I am moving this charge from infinity to this point. So I have to apply a force. I have to apply a force against what? Against the electrical field force. Understood? Okay. Okay, so the total forces or the net forces that are acting on this charge are nothing but what? F electrical and F external. So the net force, what are the total forces or the net force that is acting on the charge here? That is nothing but due to electrical field force, and another one is what? External agent. Okay, the force applied by the external agent plus the force due to electric field. So this is equal to what? This net force must be equal to what? This net force is equivalent to 0. The net force must be equal to 0 because we are assuming that there is no change in velocity. Okay, so now in this case, what will happen here? F external is equivalent to what? Is equivalent to F electrical. Understood? So finally we will end up with this condition. We will end up with this condition. Yes or no? Okay. So we got this condition here. F external is equal to what? Is equal to minus F electrical. Understood? Okay. Okay. Now, so I have moved the charge from infinity to this point. So the charge is located at this point. So now the force acting on this charge, what are the forces that are acting? One is electrical force. So this charge distribution is going to set up some electric field here. So this field force is acting in this direction. So the field force is acting in this direction, that is Fe, and external force is going to act in this direction. So the external force is acting in this direction. So the net force on the object must be equal to what? Equal to 0. So this F external must be equal to what? Minus Fe. Understood? Okay. Okay, yeah. Okay, 1 minute. So Parasmoon, if net force is not equal to 0, then what will happen to charge in the system? Yes sir, that will become another case. See, in the previous session I have explained two cases. One is if the velocity is not changing with respect to time, then in that case the net force acting on the object will be equal to 0. If the velocity changes, that means I have taken another case, that is if you throw the ball here, if you throw the ball in upward direction, so then what are the forces that are acting on the object? Only one force is going to act on the object, that is gravitational field force. Yes or no? So in that case, what will happen? What will happen here? The velocity is going to change or not? See, whenever the net force acting on the object is not equal to 0, then what will happen? Then its velocity is automatically going to change. Understood? So that means its kinetic energy is going to change. So that will be another case here. We will deal with that case also. Don't worry about that. Okay? Okay. So first we will go one by one here. So this is case 1 we are studying. Understood? Okay? Okay. Okay, yeah. So now so now here we have determined the work done by what? The work done by the external force. So what is the work done by the external agent here? In moving the charge from infinity to what? From infinity to R. So Parasmoon, we will see that case also here. Don't worry about that. Right? See, I have explained case 1 and case 2. Yes or no? In case 1, we are assuming that we are moving the charge. We are moving the charge by maintaining the constant velocity. That means velocity is approximately equal to 0. Understood? So this is the assumption and approximations we are making. Okay. See here. Now. So work done by the external agent in moving the charge from infinity to r is equal to what here? Is equivalent to. So what is the force applied by the external agent? Is nothing but F external. So let us say you have moved the charge over a small differential displacement dr bar, then the work done is nothing but F external dot what? Dot dr bar. So this is the work done by the external agent in order to move the charge against the in the field over a small differential displacement dr bar. Now if you want to determine the work done by the external agent in moving the charge from infinity to r, then what you have to do? You have to integrate from where to where? From infinity to what? From infinity to r. See, why we have made these approximations and all these things here is, see, I don't know what is the external force I have applied. Yes or no? Yes or no here? So I don't know what is the external force I have applied, but I can determine what? But I can determine electric field force. Understood? Because of this assumption, I can consider this external field force, external force is equivalent to what? Is equivalent to minus of what? Electrical force. Understood? Okay. So now I can replace, if I want to calculate this work done, I can replace this external force with what? With electrical force. Understood? So I am relating the external force with what? Electrical force. Here, since the net force is equal to 0, the external force must be equivalent to what? Minus of field force. Understood? So this one I can write it as what here? This one I can write it as, so this one I can write it as integral infinity to r. So F external I am replacing with what? Minus F electrical dot what? Dot dr bar. See, while doing the line integration, I am specifying this point again and again. Okay, so always consider this as what here? This dr bar always as what? Always as positive here. Always, whenever you are doing the line integration, always consider this as what? This as positive. So dr bar or dl bar, whatever it may be, so always you have to consider this as positive. Why? Means the direction of this dr bar will be taken care by what? Will be taken care by these limits. Yes or no? Okay. So here dr bar, so the direction of dr bar will be taken care by these limits. So always consider dr bar as what? Positive only. Understood? Okay. So this one I am specifying every time here, right? Okay. So I have explained already all these things while dealing with circulation. Yes or no? Next, see here. So this is equivalent to, so I can write this as minus of integral infinity to r f l fe dot what? Fe dot dr bar. Now if I want to make this expression independent of minus here, okay, so if I want to remove minus sign, what I can do? So I can interchange these limits. Yes or no? I can interchange the limits of this integration. So now if I take out minus here, if I take out minus, then I can interchange these limits as what here? As r to what? R to infinity. Yes or no? You are having minus integral fe bar dot dr bar infinity to r. If I want to remove this minus, then I have to change this what? I have to change this I have to interchange these limits. Yes or no? Now I have taken it as what? R to infinity. Understood? Okay. So in this manner I can represent here. So therefore the work done by the external agent. So the work done by the external agent in moving from infinity to r is equal to what? Is equal to, I can write in this manner. Yes or no? So this is the work done by the external agent. Okay. Okay. Now similarly we can determine the work done by what? The work done by the electric field force while moving the charge from infinity to this location. So whenever the charge is moving in this direction and the electrical field force is acting in this direction. Yes or no? See, I have told everything analogy. With respect to what? Gravitational field force. So compare that one and this one. You will get clarity. Understood? Okay. So that's why I have explained all those analogy with respect to gravitational field and all these things. Okay. So there gravitational field and here electric field. Understood? Both are nothing but what? Both are nothing but conservative fields. So their properties are going to be same. So that's why I have spent that much of time on that analogy. Understood? Okay. Okay, yeah. So here whenever the charge is moving in this direction, the electrical field force is acting in this direction and the displacement is in this direction. Understood? Okay. So now you want to determine the work done by the field, the work done by the field. So what is the work done by the field here? How you can write? Tell me. So the work done by the field, the work done by the field. If you want to determine the work done by the field while moving the charge from where to where? From infinity to R. So this is equivalent to what? This is equivalent to F electrical dot what? Dot dr bar, and you are moving the charge from where to where? From infinity to what? From infinity to R. So this is the work done. This is work done by the field in moving the charge, from infinity to what? Infinity to R. Understood? Now if you observe, this is the work done by the external agent, and this is the work done by what? Work done by the field, work done by the field. Understood? Now what is the total work done or net work done? See, I have told already in the previous session. See, in this case, so whenever there is no change in velocity and whenever the change in kinetic energy is equal to 0, so these are the conditions. And also I have told that the net work done or total work done, the net work done or total work done in this case will be equal to what? Will be equal to 0. Yes or no? The net work done or total work done in this case is equal to 0. That means the work done by all the forces must be equal to what? Must be equal to 0. Understood? Let us check whether we are getting that one or not. Here, what are the forces that are acting? One is electrical field force, another one is what? External. One is electrical field force, another one is work done by the external agent. Yes or no? So this is the work done by the external agent and this is the work done by the field force. Now what is the total work done or net work done here? So the total work done or net work done, the total work done or net work done by all the forces must be equal to what? This is equal to the work done by the external agent in moving the charge from infinity to R plus the work done by what? The work done by the field force in moving the charge from infinity to R. Okay. So then what you are going to get? Tell me. So if you add up these two here, if you add up these two, what you are going to get? Tell me here. So tell me, Parasmoon, Alok Kumar, good afternoon dear. So tell me here, what you are going to get? If you add these two, what you are going to get? See, this is integral R to infinity F E bar dot dr bar. Yes or no? Actually this is the work done by what? External agent. So we have replaced F external with minus Fe. So then we have written in this manner. And here this is the work done by what? This is the work done by the field force. Understood? So if you add up this one and this one, then you are going to get the net work done or total work done. So this is equivalent to what? What you are going to get? Tell me. It must be equal to 0. Yes or no? See, here the range is from R to infinity and here the range is from infinity to R. So if you add up these two, what you are going to get? Finally you are going to get this must be equal to what? This must be equal to 0. Understood? See, this is not new one here. Already we have studied all these things in the previous sessions. Understood? Okay. So you have to correlate those things with this one. Okay. So as it is I have mentioned it for a gravitational field and here it is for electrostatic field, so don't neglect all those topics. Understood? So whatever I have explained in terms of gravitational field, each and everything we can correlate that to what? We can relate that to electric field. So that's why I have thought that I have taken that analogy with respect to gravitational field because the students can easily understand that. Okay, so that's why I have taken that analogy. Understood? So now don't worry about positive signs, negative signs, everything will be taken care here. Everything will be taken care if you just follow what? If you just follow the procedure or if you just follow the concept. Understood? Okay, so and one thing you have to remember that always the work done in this case always the work done by the external agent is equal to what? Is equal to, so the net work done will be equal to 0. So that means this will be equal to 0. So if you equate W external and W field from infinity to R is equal to 0. So we can write work done by the external agent, in moving from infinity to r is equal to minus of what? Minus of work done by the field in moving from infinity to r. Understood? Okay. So this is the conclusion we can make. So whenever they ask to determine the work done by the external agent or work done by the field, okay, so there is no need to determine both here. So if you determine one, okay, that means if you determine the work done by external agent, then automatically you can determine what? You can determine the work done by the field also. Just what you have to do, if you multiply this with minus, you are going to get what? You are going to get work done by the field also. Understood? Okay. So what I have told, in generally they are not going to mention, in general in most of the questions they are not mentioning like work done by the external agent or work done by the field like that. So in that case, what I have told, by default you have to consider always the work done by what? Work done by external agent. Understood? Okay. So these things you have to understand here. Now okay, so from here onwards what we will do is since we can relate the work done by external agent and work done by field, so from here onwards we try to determine the work done by what? Work done by external agent. Understood? So if they ask to determine work done by field also, what we can do, just multiply the work done by external agent with minus, then you are going to get the work done by field. Understood? So we'll follow only one thing, that is in most of the cases they are asking to determine by the external agent, so we follow that one here. Okay. So from here onwards we try to determine what? We try to determine the work done by external agent. So from infinity to r, so what we got? Integral r to infinity f electrical dot what? Dot dr r. Understood? Okay. Now see here, now this is initial position we have considered as infinity, and final position we have considered as r. So always we will consider infinity as our reference point here. Always we will consider the infinity as our reference point. So if I say the potential energy at r, if I say something, okay, so you always define that potential energy with respect to what? With respect to some reference point here. So how we got the potential energy at r here? By moving the charge from infinity to what? By doing the work, or in moving the charge from infinity to what? Infinity to that point r. So whatever the work you have done in moving the charge from infinity to r, that is developed as what? That is developed as potential energy. So this is not the potential energy exactly at that point. This is the potential energy you have obtained in moving the charge from infinity to that point. Understood? Okay. So that means the potential energy at a point is not defined. The potential energy always defined with respect to some reference point. So what is the potential energy at a point means what is the potential energy you have gained at this point in moving the charge from infinity to that point. Understood? Okay. So absolute values of potential energy is meaningless. Understood? Okay. So always it is defined with respect to some reference. So that reference point we are going to consider it as what here? We are going to consider our reference point as infinity. So if I ask you what is the potential energy at a point, what do I mean by that here? What is the potential energy I have gained in moving the charge from infinity to that point? Understood? So always I will tell gain in potential energy. So if we got gain in potential energy as positive, then it is taken as gain. It is taken as gain itself. Understood? If suppose if we got gain in potential energy as negative, then you have to consider that potential energy as what here? That potential as what? That potential energy as lost in potential energy. See, it is just like if I say you are getting a profit of 10 rupees. If I say you got a profit of if I say I got a profit of 10 rupees, what do I mean by that here? So whatever the investment I have done, so apart from that I got some profit, that is 10 rupees. Yes or no? Okay. If I say I got profit of minus 10 rupees. So what do I mean by that? So profit of minus 10 rupees means I have lost what? I have lost 10 rupees. Understood? So in that manner also I can specify it or not, yes or no? So in the same manner here, so always we will consider the potential energy as gain in potential energy as you move the charge from infinity to that point. Understood? Okay, but if that gain in potential energy we got it as positive, then it is going to be taken as gain itself. Understood? If suppose we got that potential energy as negative, then we have to consider that potential energy as what here, lost in potential energy. Understood? Okay. Okay, so if we do some problems, then you will get some more clarity on this. Okay, so I hope each and everything is clear here. So now here I am explaining this one, yes or no? So here the initial position is infinity and the final position is what, r. Now here whenever you are integrating, what you are doing, so this is the final position and this is the initial position. So that means if you want to determine the work done by the external agent in moving the charge from A to B, then how you have to write here? So just follow the same thing here, So here this is initial and this is final. So what you have to write? So you have to write integral b to what? Integral b to a fe bar dot what? Dot dr bar. Understood? So this is nothing but final and this is initial. So in this manner we are going to write the work done here. Okay, this is the convention we are going to follow throughout our subject. Understood? Okay. Okay. So now then we have determined by taking a charge capital Q. So we have taken a charge capital Q. So this is fixed at this location. So whenever it is fixed at this location, it is going to set up some electric field. Yes or no? It is going to set up some electric field. Now what is the work done in order to bring a charge which is at infinity to a distance r. So what is the work done in order to bring that charge from infinity to a distance r? So let us say the charge is you have taken from infinity to this point. So now what is the potential energy you have gained here? What is the potential energy you have gained in order to move the charge from infinity to this point? So that is nothing but yesterday in the previous session we have determined here. So that is the work done by the external agent in moving the charge from infinity to r. Is equal to what? Is equal to what we got here? So this is integral r to infinity f e bar dot d bar. Now Fe is nothing but what? The force experienced by this charge. So it is going to point in this direction. So external force is going to act in this direction. Understood? Okay. So what is the electrical force here acting on this charge? That is nothing but what? That is nothing but QQ by 4 pi epsilon r square. It is going to point in AR cap direction. So this dr I told always take it as positive. So dot dr AR cap. Understood? So if you solve this integration here, that is integral r to infinity QQ by 4 pi epsilon r square. So this dot product will get simplified and then it will become QQ by 4 pi epsilon r square dr. So if you solve this integration, what we got here? QQ by 4 pi epsilon into r. So this is the work done by the external agent in moving the charge from infinity to what? From infinity to r. So what are the units of work done here? The units of work done is nothing but what? Is nothing but joules. Yes or no? Okay. Okay, yeah. So that means whenever you are having a charge q here and another point charge q here, which are separated by r. Okay, so in order to assemble these charges in this manner, we have to do some work or not? Yes or no? We have done some work. So whatever the work we have done in order to assemble these charges at this location, so that work done will be stored as what? Potential energy. So what is the potential energy stored in this system of two charges here? So that is nothing but what? That is nothing but QQ by 4 pi epsilon into r. So whatever the work you have done, that will be stored as potential energy. So this work done is also called as what? Is also called as potential energy. Understood? So whenever you are having 2 point charges, the potential energy is nothing but what? Is nothing but QQ by 4 pi epsilon into R. Understood? Okay? Okay, yeah. So next, see here, one more point I want to specify here is, see, the work done or energy, okay. So all these are nothing but what? These are nothing but a scalar quantity or vector quantity. See, this work done is a resultant of what? Is a resultant of force dot displacement. So that means it is a resultant of dot product. So that means the work done is what? Is a scalar quantity. Is a scalar quantity. So in the first class itself, I have told that energy or work done is a scalar quantity. Yes or no? Because it is the resultant of what? Force dot displacement. Understood? Okay. Okay, yeah. So depending upon the charge distribution here, depending upon the charge distribution, this F bar is going to change. See, if I change this charge distribution, if suppose if I place some infinite sheet charge, or if I place line charge, or if I place some spherical charge distribution, so then accordingly the field surrounding that charge distribution is going to change. Then accordingly the force experienced by this charge Q is also going to change. Okay, so if I place simply a point charge, then in that case the potential energy or the work done to move the charge from infinity to that point is given by QQ by 4 pi epsilon into R. Understood? Okay. Okay, yeah. So now see here. So next we have done one problem here. So that is, we have placed 3 identical point charges we have placed, and the successive distance between them I have taken as 1 meter, and in another case I have taken the charges 3 identical point charges such that the successive distance between them is 0.5 meters. Understood? So in this case, the potential energy stored in the system, I am considering it as W1, and in this case the potential energy stored in the system, I have considered it as what? W2. Understood? So we have determined the relation between W2 and W1. So what we can conclude just by looking at this diagram here. So if you are placing the charges closely here, so if you want to place the charges closely, then you have to do more and more work. Yes or no? Yes or no? See, if I am having some charge here, now I want to move another charge from infinity to this point here. Okay, so I have to do some work in order to move that charge from infinity to this point. Why I am doing work? Because whatever the charge I have placed here, it has set up some field in its vicinity, and that field is going to exert the forces on other charges. Yes or no? So against that force, I have to move the charge. So that's why I have to do some work in order to move the charge. Understood? Okay, so whatever the work I am doing, that is going to develop as what? Potential energy in the system. So now I have moved that charge to this location. Now the potential energy in the system is something. Understood? Now if I want to move further here, so whenever I am moving further, the repulsive force is going to be more or not? Yes or no? Or the force exerting by this charge distribution is going to be more. So that means against that force, if I want to move, I have to do more work. Yes or no? So if I do more work, then the potential energy that is going to develop is also going to be more. Yes or no? So if I move further and further and further, I have to do more and more and more work, and hence the energy, the potential energy in the system is going to increase. Understood? So if you want to place the charges very closely, then you have to do more and more work. Understood? Okay, so that means here in this case you have to do more work when compared to this one, so you can directly tell in this case W2 must be greater than what? W1, and we have derived the exact relation, that is W2 is equal to what? W2 is equal to 2 times of what? 2 times of W1. So this is what we have done in the previous session. This problem we have solved. Understood? Okay. Okay, so here electrostatic field is a conservative field, and you have to remember what are the properties of a conservative field. So the work done doesn't depend upon the path you are moving. It depends only upon what? Initial and final points. That is the first one. Another one is what? The work done around any closed path in a conservative field must be always equal to 0. Understood? Okay, our electrostatic field is also a conservative field. I am going to prove that here. I am going to prove that. Okay, so until that, so I am going to prove that anyway our electrostatic field is a conservative field. So until that, take it as granted that electrostatic field is a conservative field. Understood? So it is going to obey all the properties of conservative field, right? Okay. So now, we try to solve some problems here. We try to solve some problems based on this, right? Okay. Now see here. So here I have given that a point charge Q is rotated along a circle in the electric field. A point charge Q is rotated along a circle in the electric field generated by another point charge capital Q. Generated by another point charge capital Q. Understood? Okay. A point charge small q is rotated in a circle in the electric field, which is produced by what? Which is generated or produced by a point charge capital Q. So then they are asking the work done by the electric field, on rotating charge in one complete revolution is. Okay, so here you are having a charge capital Q, so it is going to set up, it has set up some electric field, it is going to set up some electric field in its vicinity, right? Now what you are doing here? So now the charge Q is rotating along a circular path in this field, okay? So let us say it is rotating in a circular path. Okay, in this circular path, let us assume it is rotating in this circular path. So let us say the charge Q is rotating in this circular path here. This charge Q is rotating in this circular path. Now they are asking what is the work done by the field, on the rotating charge in one complete revolution. Okay, tell me here. So I have given the options. So 0, positive, negative, 0 if the charge Q is at the center and non-zero otherwise. Okay, so these are the options I have given. So tell me here. So you are having a point charge capital Q, okay? So it is going to set up some electric field. So in that field, a charge small q is revolving around that charge in a circular path, Understood? Then what is the work done by the field? On this moving charge over one complete revolution, So that's what they are asking. So tell me here, what is the answer? Parasmoon, Alok Kumar, tell me. Amruta Anil, good afternoon. Nero Lakshmi, good afternoon. Okay, tell me the answer here. I am expecting from your side. Parasmoon, Alok Kumar, Nero Lakshmi, tell me the answer here. Amruta Anil, I have given options also here. At least tell some option. I have given A, B, C, D, na. At least tell some option here. A, B, C, D. Which one is correct? See, what is the work done by the field around any closed path here? This is conservative field or not? Yes or no? So, what is the work done by the field around any closed path in a conservative field? Tell me here now. What is the work done by the field on the charge over this one complete revolution? So, that means they are asking indirectly what is the work done by the field on the charge by over one complete revolution. That means you have to determine the work done around this closed path. So, what is the work done around any closed path here in a conservative field? That is always equivalent to what? Always equal to 0. Yes or no? Okay. So, you can directly tell the answer is what? The answer is 0. Why here? Since work done around any closed path must be equal to what? Must be equal to 0. So, this is one way, and I will tell another way also. See here, the field here is, we know that due to this point charge, the field is going to point in which direction here? In radial direction. Yes or no? So, that means it is going to point in AR cap direction, and the charge is moving along the circumference of the circle. Yes or no? It is moving along the circular path. Understood? So, that means the displacement of the charge is along the circumference of the circle. So, that means I can say the displacement of the charge is in which direction? Is in A phi cap direction, and the field is in which direction? AR cap direction. So, the force, the electrical force is in AR cap direction, and the displacement is in which direction? The displacement is in A phi cap direction. Yes or no here? Since the charge is moving along the circumference of the circle, means it is moving along A phi cap direction. Yes or no? So, if the charge is present at this location, here it is going to be A phi cap, and here the force direction is going to point in this direction. Understood? So, at each and every point here, on the circumference of the circle, everywhere the electric field is pointing radially outward, and the charge is moving, that is the displacement is in which direction? Along A phi cap direction, Yes or no? So, the charge is moving along A phi cap direction, and the force is in AR cap direction. So, that means the force direction and the displacement direction, both are what? Both are perpendicular to one another. So, in that case also, what is the work done? Work done will be 0. Yes or no? So, force dot displacement is nothing but work done. Here at each and every point, the force direction and the displacement direction, both are perpendicular to one another. So, and hence here also the work done will be equal to what? Work done will be equal to 0. So, in that manner also we can conclude that the work done will be what? The work done will be equal to 0. Understood? Okay. Okay. Next problem. So, now see here. So, what is the question they have given here? So, they have given that three particles each having a charge of 10 microcoulombs. So, three particles each having a charge of 10 microcoulombs are placed at the vertices of an equilateral triangle, of side 10 centimeters. Find the work done by a person, that means external agent here. Find the work done by a person in pulling them apart to infinite separations. Find the work done by a person in pulling them apart to infinite separations. So, what is the question they are asking here? What is the question they are asking? See here. So, they have placed here, three identical charges. Okay, so they have placed three identical charges, let us say here Q and here Q and here Q, at the vertices of what? At the vertices of an equilateral triangle of side how much here? 10 centimeters. So the side of equilateral triangle is 10 centimeters. So this is 10 centimeters means this is also 10 centimeters, this is also 10 centimeters, because it is an equilateral triangle. So the value of Q here is equal to what? Is equal to 10 microcoulombs, 10 microcoulombs. Understood? So the value of Q here 10 microcoulomb, here 10 microcoulomb, here 10 microcoulomb. So here what they are asking is three particles each having a charge of 10 microcoulomb are placed at the vertices of an equilateral triangle of side 10 centimeters. Find the work done by a person in pulling them apart to infinite separations. Now if you want to pull these charges here, if you want to pull these charges away from one another to infinite separations, to infinite separation. Understood? So then what is the work done by the external agent? What is the work done by the external agent in order to pull these charges to infinite separations? Understood? Okay, so I am expecting the answer from your side here. So I will give 1 minute time here. I will give 1 minute time. Okay, so 1 minute is very much here. Okay, take 1 minute time here. So within 1 minute I am expecting some answer from you. Okay. Okay. See, they are not asking to determine the work done in order to assemble the charges at these locations. What they are asking, what is the work done by the external agent in order to move these charges away from one another, such that the distance between one another must go to what? Must go to infinite. Understood? Okay. That means they are asking what is the work done in order to move this charge from here to infinity, from here to infinity, and from here to infinity. So that is what they are asking. Tell me here. Parasmoon, Alok Kumar. It is very simple problem here. Just I am expecting some answer from you. Tell me. Music is motivation. Clear? Okay. Tell me here, what is the answer for this problem? At least tell some number or something. See, it doesn't matter whether you are saying right answer or wrong answer here, but at least you have to try and tell me some answer. Okay, so last 20 seconds here. So I will wait last 20 seconds. Okay. Okay. So it's my turn to solve the problem, right? Okay, fine. See here. See, first what I will do here is I will try to determine the work done by the external agent in order to assemble these charges here. First I will try to determine the work done by the external agent in order to assemble these charges. Yes or no? Okay. So now first let us consider I am naming this as 1 and this as 2 and this as 3. Understood? Okay. Now I have taken this charge. Now let us assume there are no charges, nothing is present here. Q2 is not present, Q3 is not present, Q1 is not present. All are present at infinity. all are present at infinity. So from that infinity distance, first I am trying to bring q1 charge. First I am trying to bring q1 charge. Since here there are no charges are present, that means there is no field here. So that means there is no field here. That means in order to bring this q charge from infinity to this point will be equal to what? Will be equal to 0. Yes or no? So if there are no charges that are present in this region, means there will be no field. So if there is no field, then there will be no repulsive forces on this charge. Understood? So I can happily bring that charge from infinity to what? From infinity to this location. Understood? So in order to bring the first charge, what is the work done here? Work done will be 0. Yes or no? So I am determining the work done by the external agent in moving the charges from infinity to what? From infinity to this locations here. From infinity to this location. Okay. In moving the charge from infinity to this location. So let us say this location is, let us say, A. Okay, from infinity to A. Understood? Next, so what is the work done here? What is the work done? Work done will be 0. Yes or no? So initially I am bringing A charge. Next, what is the work done in order to bring? What is the work done in order to bring Q2 charge? Q2 charge. So here this is for Q1 charge and this is for Q2 charge. Now whenever I am bringing Q2 charge, already Q1 charge is present at location A. So let us say this location is B and let us say this location is C. Understood? So while if I want to bring Q charge, then I have to, that means if I try to bring Q2 charge, then I have to do the work against what? Against the field set up by this Q1 charge. Yes or no? Okay. So I have moved this charge from infinity to this location. Then what is the work I have done in order to move this Q2 from infinity to this location here? Already this charge is present. So this charge is going to set up some electric field. So against that field, I am moving this charge from infinity to this location. Understood? So now I have brought this charge from infinity to this location. Now in the system, I am having these two charges. Yes or no? So whenever you are having 2 point charges, what is the work done here? So already we have derived that one. So what is the work done? Is equal to what? So here I have brought from infinity to what? Infinity to B. So that is equal to what? That is equal to Q square by what? Whenever you are having 2 point charges. Understood? Okay. So separated by distance. The distance from here to here is 10 centimeters. So what is the work done? Q square by 4 pi epsilon. Let us take epsilon naught. Okay. 4 pi epsilon naught into what? Into 10 centimeters. 10 centimeters. Understood? So Q square by 4 pi epsilon naught into R. Next, in order to bring Q3 charge, what is the work I have to do? So the work done by the external agent in order to move from infinity to C. Now you have to do the work in order to bring Q3 charge. You have to do the work against Q2 as well as what? Against Q1. So if you are doing the work against Q1, then what is the work done against Q1 here? That is nothing but Q square by what? Q square by 4 pi epsilon naught into the distance from here to here is also nothing but what? Is also nothing but 10 centimeters. Yes or no? So 4 pi epsilon naught into 10 centimeter. Next, you have to do the work against what? Against Q2 also or not? Yes or no? Now Q1 and Q2 are present. Now you are trying to bring Q3 from infinity. So you have to do the work against Q1 as well as what? Q2. So against Q1 we got Q square by 4 pi epsilon naught 10 centimeters plus against Q2 you will get Q square by 4 pi epsilon naught. What is the distance from here to here? Is also nothing but 10 centimeters. Understood? So this is the work done in order to bring Q1 is 0, the work done in order to bring Q2 is this much, and the work done in order to bring Q3 is this much. Okay, so finally what is the total work done here? What is the total work done by the external agent? So the total work done by the external agent in moving from infinity to these points. Okay, so what is the total work done here? So total work done by the external agent is equal to what? Is equal to, you have to add up all these all this work done. Yes or no? Here it is 0 plus q square by 4 pi epsilon naught. Here q square by 4 pi epsilon naught 10 centimeters. Here also q square by 4 pi epsilon naught 10 centimeters. So this value is same, this value is same, this value is also same. So if I add up, so I can write directly 3 into q square by 4 pi epsilon naught into what? Epsilon naught into 10 centimeters. So this is equal to 3 into what is q value here? Q value they have given as 10 microcoulomb. Yes or no? They have given as 10 microcoulomb. Right? 10 microcoulomb. Okay, so 3 into 10 microcoulomb, that is 10 into 10 power minus 6 whole square divided by what? Divided by 10 centimeters. 10 centimeters, I can write it as 10 into 10 power minus 2 meters, and 1 by 4 pi epsilon naught value here. We know 1 by 4 pi epsilon naught value. What is the value of 1 by 4 pi epsilon naught? Is nothing but 9 into what? 9 into 10 power 9. So this is the value of what? This is the value of 1 by 4 pi epsilon naught. Understood? Okay. Now if you do this, so this is the work done here in joules. So if you do this, what you are going to get here? Tell me. So here you will get here 3 into 10 square, that is 10 square into 10 power minus 12 into 9 into 10 power 9 divided by 10 into 10 power minus 2. Okay. Okay. So if you do this, what you are going to get? 10 here, here 10. So if you take 10 power minus 2 to the numerator, so then you will get 10 power minus 10 here. If you take 10 power minus 2 to the numerator, you will get 10 power minus 10. Here 10 power 9, right? Okay. So here 10 power minus 9 will get cancelled. So you will have only 10 power minus 1 here, 10 power minus 1. So 10 power minus 1 here and 10 here will get cancelled. So 3 into 9, how much here? 27 joules. 27 joules. So this is the work done by the external agent in order to assemble these charges. In order to assemble these charges at the vertices of what? At the vertices of an equilateral triangle. Yes or no? But what they are asking here? What they are asking? They are asking to determine the work done in order to move these charges to what? To infinite separation. Yes or no? Okay. See, we know that you have brought this charge. You have brought this charge Q1 from infinity to what? From infinity to this location. So the work done in order to move the charge from infinity to A. Understood? Now what they are asking here? What they are asking? To determine the work done in order to move these charges from these locations to infinity. Understood? Okay. Now see here. So if you move this charge from location A to infinity. Understood? So you have moved from infinity to A. Now you are moving this charge from A to infinity. So that is work done in order to move the charge from A to infinity. Next, you brought this charge Q2. You brought this charge Q2 from where here? From infinity okay. So now you brought this charge Q2 from where? From infinity to this location. So work done in order to move the charge from infinity to B. Now they are asking to determine what is the work done in order to move this charge from B to what? From B to infinity. That means you have to determine the work done in order to move the charge from B to infinity. Similarly, we have taken this charge from infinity to this point. So that is the work done in order to move the charge from infinity to C. They are asking to determine the work done in order to move the charge from C to what? C to infinity. Understood? Okay. So here infinity to A and infinity to B and infinity to C is nothing but the total work done in order to assemble the charges. Yes or no? So the work done in order to move this charge from A to infinity, from B to infinity, from C to infinity is nothing but the work done in order to separate the charges to infinity. Understood? Okay, so that means here, if you observe here, the work done around this closed path, must be equal to what? Here it must be equal to 0. Here also it must be equal to 0. Here also it must be equal to 0. Understood? Okay, so here what I can write here, see here. Okay, see here. So this is the work done here. This is the work done by the external agent in order to assemble the charges. Yes or no? So here we have determined the work done by the external agent, total work done in order to assemble. Yes or no? In order to assemble the charges. So this is the work done we got. But they are asking what is the work done in order to separate the charges. Yes or no? So work done to assemble the charges is nothing but what? Is nothing but work done from infinity to A plus work done from infinity to B plus what? Work done from work done from infinity to A plus infinity to B plus infinity to C. Yes or no? So this is what we got. As what here? This is what we got as 27 joules. Understood? But what they are asking? They are asking what is the work done in order to move these charges to infinity. So that means work done in order to move the charge from A to infinity plus B to infinity plus what? Plus C to infinity. So this is what they are asking, right? Okay, so this is the work done to assemble the charges and this is the work done for separation of charges. Understood? Okay, so if you add up these two here, so that is work done to assemble plus work done for separation. So this must be equal to what? See, if you add up these two, you are going to get what? Work done from infinity to A plus what? Work done from A to infinity. So that means it represents the work done around any closed path. So that means if you add up these two, you are going to get 0. Similarly, if you add up these two, you are going to get 0. Similarly, if you add up these two, you are going to get what? You are going to get 0. So that means if you add up work done in order to assemble the charges and if you add up work done for separation of charges, this must be equal to what? This must be equal to 0. So therefore the work done in order to separate the charges here, must be equal to what? Minus of work done to assemble the charges. So that is equivalent to what? That is equivalent to minus 27 joules, right? So this must be equal to minus 27 joules. Understood? Okay, so we can directly tell here because the work done to assemble is 27 joules, means the work done to for separation is nothing but minus 27 joules. That we can tell directly, but I want to explain this clearly, so I have taken all these things here. So it is just like a revision that everywhere the work done around any closed path must be equal to 0. Understood? Okay, so the work done for separation is equal to what? Is equal to minus 27 joules. So the answer for this question is not 27 joules. It is nothing but what? Minus 27 joules. Understood? Okay. Okay. Yeah. So Venkatesh Gopal, if they are attracting charges, how will it affect work done? I will tell here, we will take each and every case, don't worry about that. See, always follow the concept here, okay, it is going to give you right result, okay. I will take different types of problems here, don't worry. So there it will get cleared, each and everything will be clear, right. So is this problem clear? Tell me. So what is the answer for this one here? It is not 27 joules, it must be what? It must be minus 27 joules. Okay, so we can tell the answer directly for this one, but I want to the analysis is very important. So I have explained each and everything. Okay, so for this problem, the work done is equal to what? Is equal to minus 27 joules. Minus 27 joules. So in order to separate the charges to infinity. So by what? By external agent. By external agent. Understood? Okay. Okay. Yeah. Next. So is this problem clear? Tell me. Is this problem clear? Yes, Venkatesh, Parasmoon, Alok Kumar. Tell me here. Is this problem clear? Yes. Tell me here. Venkatesh, Alok Kumar, music is motivation, Parasmoon. Tell me, is this problem clear? Yes or no, yaar? Tell me. Okay, clear. Okay, fine. Next. So this question is given in GATE here. So this question is given in GATE. Okay. So here, what is the question they are asking here? So an electron Q1 is moving in free space with velocity 10 power 5 meters per second, with velocity 10 power 5 meter per second towards a stationary electron Q2, towards a stationary electron Q2 far away. The closest distance that this moving charge, that this moving electron gets to the stationary electron, before the repulsive force, diverts its path is. Okay, so what they are asking, an electron Q1 is moving in free space with velocity 10 to the power of 5 meters per second towards a stationary electron which is far away. The closest distance that this moving electron gets to the stationary electron before the repulsive force diverts its path is. Now tell me here, what they are saying here is, here you are having a stationary electron. Let us say Q2 is nothing but what? Q2 is nothing but a stationary electron here. So you are having a stationary electron Q2 here. Understood? Now from far away from Q2, okay, so let us say very far away here, very far away from Q2. So you are having another electron which is nothing but what? Which is nothing but Q1, and its velocity, the velocity with which this Q1 is moving is nothing but what? Is nothing but V is equal to 10 to the power of 5 meters per second. 10 to the power of 5 meters per second. Understood? Okay, so at very far away from Q2 you are having Q1. So that means whenever they are saying far away means, what do you mean by that here? What do you mean by that means, this Q1 is not going to experience any field, is not going to experience any field that is exerted by what? That is produced by Q2. So Q2 is present here and Q1 is present very far away from what? Far away from Q1. So that means at that far away distance, the force experienced by Q1 due to the field produced by Q2 will be almost what? Will be almost negligible. So that's what they mean by far away. Understood? So at that far away distance, initially the velocity of that charge is 10 power 5 meters per second, and it is moving towards what? It is moving towards what? It is moving towards Q2 with velocity v equal to 10 to the power of 5 meters per second. So here you are having Q2 and here you are having Q1. So Q1 is coming from far away distance. So far away distance means here there is no effect of field produced by Q2. Understood? So at that location it is moving with velocity v equal to 10 to the power of 5 meters per second. Understood? Now here Q2 is present. So whenever here Q2 is present means Q2 is present means it is going to set up what? It is going to set up some field in its vicinity. Understood? Okay. So now this Q1 is trying to move towards what? Towards Q2. So whenever it is moving towards Q2 here, what happens to velocity of Q1 here? Tell me. What happens to the velocity of Q1? Here nobody is moving the charge Q1 towards Q2. Yes or no? So it is projected with some velocity v from far away distance. Now it is moving on its own towards what? Towards Q2. Yes or no? It is moving with velocity v equal to 10 to the power of 5 meters per second towards what? Towards Q2. So whenever it is moving towards Q2, it is going to enter into what? It is going to enter into the field produced by what? Produced by Q2. Then what happens to the velocity of Q1 here? What happens to the velocity of Q1? See, this will come under what? This will come under case 2 here. See, in case 2, while explaining the analogy with respect to gravitational field, what I have told here, if you throw the ball into the space, yes or no? If you throw the ball in upward direction, so initially you are providing some velocity to that ball. Yes or no? Now as the ball moves up here, what happens to its velocity? Its velocity is going to decrease. Why it is decreasing? Because the gravitational field force is going to act against what? Against the movement of what? Against the movement of ball. Yes or no? So since the gravitational field force is acting in downward direction, as the ball moves in upward direction, its velocity will gradually decreases and reaches to what? And reaches to 0. Understood? Okay, so here only one force is acting on the object, that is gravitational field force. So here also the same scenario or not? Yes or no? Here you are having Q2 and Q1 is projected with given some initial velocity, that is v 10 power 5 meters per second. So it starts moving with 10 power 5 meters per second and it is moving towards Q2. So as it moves towards Q2, it is going to enter into the field that is produced by Q2. So what this field is going to do, since Q2 is electron, Q1 is also electron, both are of same polarity, so they are going to repel each other. Yes or no? But they are saying that Q2 is stationary. Q2 must be fixed at this location. Understood? Now Q1 is moving towards Q2. So once it enters into the field produced by Q2, what will happen here? Since both are of same polarity, it is going to repel this Q1 or not? Yes or no? So against this repulsive force, this Q1 is trying to move towards what? Towards Q2. So as it moves towards Q2 here, what happens to the velocity? What happens to the velocity of Q1? Tell me. Parasmo. Yes, the velocity is going to decrease. So now you have to correlate that analogy with respect with this one here, the analogy of gravitational field, whatever I have explained, you have to correlate that one to this. Understood? Okay, so Q2 is present here. Now the charge is moving towards what? Towards Q2. Q1 is moving towards Q2. So as it moves towards Q2, its velocity is going to what? Its velocity is going to decrease, and at one position, what will happen here? At one situation, its velocity will completely become what? Completely become equal to 0. So once the velocity becomes equal to 0, then then it is going to move in which direction? Here Q2 is present, yes or no? Q1 is moving towards Q1, Q1 is moving towards Q2, its velocity is decreasing and becomes equal to 0. Yes or no? Now once it becomes 0, then what will happen here? Then what will happen? So this Q2 is exerting a repulsive force on this Q1 or not? So what will happen? So this Q1 will start again moving away from what? Away from Q2. Yes or no? Understood? See, it is just like if you throw the ball, so its velocity decreases and reaches to 0. So once it becomes 0, then it starts moving towards what? Towards the surface of Earth. So it changes its direction and moves towards the surface of Earth. So here also the same thing here. So its velocity is going to decrease and becomes equal to 0. So once it becomes 0, then what will happen here? So because of the repulsive force produced by Q2, so this Q1 will start moving away from what? Away from Q2. Yes or no? That means it is going to divert its path. So that means whenever the velocity is becoming equal to 0, that is the minimum distance. Yes or no? That is the minimum distance between what? Between Q2 and Q1. So after that, what will happen? Again, the distance between Q2 and Q1 is going to increase. Yes or no? So they are asking what is the minimum distance? What is the minimum distance between Q1 and Q2? Understood? Okay. Okay, so an electron Q1 is moving in free space with velocity 10 power 5 meters per second towards a stationary electron Q2, which is far away. The closest distance, that means they are asking the minimum distance or closest distance that this moving electron gets to the stationary electron before the repulsive force diverts its path. That means before it diverts its path means at that location its velocity is going to become what? Is going to become equal to 0. So once it becomes equal to 0, then after that what will happen? It is going to divert its path. Understood? So before diverting its path, what is the closest distance between Q2 and Q1? So that's what they are asking here. Okay, so I hope you have understood. You have understood this problem here, right? Okay. Okay. So now so now we know that from law of conservation of energy, the total energy must be conserved throughout this time. Yes or no? Okay. Now initially the charge is moving, the charge is having a velocity v equal to 10 to the power of 5 meters per second. That means it is having what here? Initially it is having a kinetic energy that I am representing with KEI. So what is the total energy here? What is the total energy initially you are having? So the total energy initially is equivalent to kinetic energy initial plus what? Plus potential energy initial. So what is the potential energy initially? See, this charge Q1, they have said that it is very far away from what? Far away from Q2. So we know that if you are having 2 point charges Q2 and Q1, what is the potential energy? Potential energy is given by what? Q1, Q2 by what? 4 pi epsilon naught into R, where R is the distance between Q1 and Q2. Since they are saying Q1 is far away from Q2, so that means R is very large here. R is very large. R is very large. Understood? So if R value is very large, then it is in denominator. So I can consider this as approximately equal to what? I can consider this as approximately equal to 0. Approximately equal to 0. So that means initially the potential energy is equal to 0, and initially the kinetic energy of the charge is nothing but what? Is nothing but half mv square. Half mv square. Here m is nothing but the mass of electron. V is nothing but velocity. So initially the total energy is in the form of what here? Is in the form of only kinetic energy. The potential energy is equal to 0. Understood? Now as it moves here, into this field produced by Q2, what will happen here? Its velocity gradually decreases. So its velocity is decreasing means the kinetic energy is decreasing. So the kinetic energy is decreasing means what here? That whatever the kinetic energy that is decreasing, that will be transformed into what? That will be transformed into potential energy. So that means the kinetic energy will gradually decreases and and the potential energy, whatever the decrease in kinetic energy, that will be transformed into what? Potential energy. So the potential energy will gradually increases. Now at one stage, what will happen here? Its kinetic energy will become equal to what? Will become equal to 0. So at this, let us assume at this location, its velocity has become equal to what? Its velocity has become equal to 0. So throughout this path here, its velocity gradually what? Gradually decreases. Its velocity gradually decreases. So that means the kinetic energy is going to decrease and the potential energy is going to increase throughout this path. Next, finally, what will happen? The velocity will become equal to 0. So the velocity will be equal to 0. So here the kinetic energy. So this is the final position. Let us say this is the final position. So the total energy at this position here, the total energy at this position must be equal to what? Must be equal to the kinetic energy final plus what? Plus the potential energy final. Understood? Okay. So now at this location, since velocity is equal to 0, so kinetic energy will be equal to 0. So the total energy must be equal to what? Must be equal to, is in the form of what? The total energy is in the form of potential energy only. Understood? Okay. So initial energy, what is the total initial energy here? Total initial energy is equal to what? Half into mEV square. So that is kinetic energy. Now what is the potential energy? Tell me, what is the potential energy? So now whenever the charge reaches to this point here, then the distance, let us say the distance from Q1 to Q2, this is the minimum distance between Q1 and Q2 or not? Yes or no? So I am representing this with R minimum. Understood? Now what is the potential energy whenever it reaches to this location here? Tell me, what is the potential energy? So Q1 Q2 divided by what? 4 pi epsilon naught into R minimum. So PEF is nothing but Q1 Q2 divided by what? Divided by 4 pi epsilon naught into R minimum. Yes or no? That is the potential energy at this point. Okay. So the total energy must be always what here? The total energy must be always conserved. So what do you mean by that? That means at any instant of time, the total energy must be what? Must be constant. Okay. So at this instant, the total energy is half mEV square, and at this instant, the total energy is Q1 Q2 by 4 pi epsilon naught R minimum. Understood? Okay. So the total energy at any instant of time must be what? Must be constant. So that is called as what? Law of conservation of energy. Understood? Okay. So initially the total energy is in the form of kinetic energy. So then what will happen here? That kinetic energy will be gradually transformed into potential energy, and finally the total energy is converted into what? Is converted into potential energy. Understood? So the initial total kinetic energy is transformed into the total potential energy finally. Okay. So at any instant of time, this total energy must be constant, that is TEI must be equal to what? Must be equal to TEF. So that is half mEV square is equal to what? Is equal to Q1 Q2 divided by what? Divided by 4 pi epsilon naught R minimum. Now here Q1 into Q2 is nothing but what? Q1 and Q2 both are electrons or not? Yes or no? So I can write it as Q square, and what is the charge on electron here? The charge on electron is nothing but what? The charge on electron is nothing but 1.6 into 10 to the power of minus 19 coulombs. Yes or no? So they have given everything here, right? Okay. So Q1, so you can write they have given in terms of E. Okay. So Q1 is equal to E, which is equal to minus 1.6 into 10 to the power of minus 19 coulomb, and Q2 is also nothing but electron. The charge on electron is minus 1.6 into 10 to the power of minus 19 coulomb, and mass of electron they have given as what? 9.11 into 10 to the power of minus 31 kg. Okay. So substitute all these values here. So here here you will get minus 1.6 into 10 to the power of minus 19 whole square. right? Okay, so 1 by 4 pi epsilon naught here, 1 by 4 pi epsilon naught is 9 into 10 power 9. So into this minus 1.6 into 10 to the power of minus 19 whole square divided by what? Divided by R minimum. Okay, so this is nothing but 1 by 4 pi epsilon naught value. Okay, next here on RHS side, half me v square, that is half into mass of electron is 9.11 into 10 to the power of minus 31 kg into v square. V is how much here? 10 power 5 meters per second. So that is 10 power 5 whole square. Understood? Okay, so this is the initial kinetic energy. Yes or no? Okay, so from here you can determine what here? You can determine R minimum. So R minimum is equal to, so 9 into 10 to the power of 9 into minus 1.6 into 10 to the power of minus 19 whole square divided by what? Divided by, if you send 2 to this side, you will get here 2, and this total term will go to denominator. So that is 9.11 into 10 to the power of minus 31 into 10 to the power of 5 whole square, that is 10 to the power of 10. Okay, okay, yes or no? Okay, so now you can do this calculation here, you can do this calculation and tell me the answer here. Simplify this one and tell me the answer. Do this calculation here. I have done everything, so tell me the answer. So the answer must be into 10 to the power of what? 10 to the power of minus 8. Yes or no? 10 to the power of minus 8. So in terms of into 10 to the power of minus 8 meters. Okay, you have to get the answer like this. So into 10 to the power of minus 8 meters. So what is the answer you have to get? Tell me. Do this calculation and tell me here. Tell me here, tell me the answer. You have to get, I think, 5.08 or something. I don't know. So please check that one. You have to get approximately 5.0678 or something like that. Okay. Yes, 2.56 into 2. 2 5 are 10. Okay, you will get approximately, answer will be approximately 5. Approximately you have to get here 5 point something here, 5 point something. So 5 point something you have to get. Okay. If anybody done this answer, please confirm that here. Please confirm this. Tell me here. Tell me here, Paras Moon. Okay, you can check this calculation. So you will get approximately 5 point something into 10 to the power of minus 8 meters. So you can check this one here. You can check this one, right? Okay. Okay. See, Venkatesh, So you have asked one doubt now. So what happens if attractive force or something? Yes or no? So already you have to go through that analogy here. So wherever I have explained about a gravitational field, okay, so go through that analogy. So that analogy is very important here, right? Okay, so see here, if you are having some charge here, let us assume some positive charge here. Okay, now if you are trying to bring, so let us consider some positive charge distribution. So just I will briefly explain here. So anyway I will explain this while taking the problems. Okay, so just I will briefly explain here. So then while doing the problems I will explain further clearly. Okay, so if you consider some positive charge distribution here, so the field is going to point like this. Understood? Now you are asking that if you try to bring a negative charge, yes or no? So if you try to bring a negative charge, then the force between this one and this one is going to be attractive force. Yes or no? See, always in this process here, whenever you are bringing the charge by external agent, understood? Okay, so in that process always you have to maintain constant velocity. Since at infinity the velocity is approximately equal, velocity you are considering it as 0, that means it is at rest you are considering, that means you have to maintain the velocity almost negligible, that means velocity must be approximately equal to 0 while bringing the charge from infinity to what? From infinity to some distance r, from infinity to some distance r. Understood? Now here the electrical force is acting in this direction here. The electric force is acting in this direction. So what I have told here, the velocity of the charge you have to maintain almost equal to what? Almost equal to 0. This is very important. Understood? So if you just so in order to maintain this velocity almost equal to 0, so what you have to do? You have to apply an external force in this direction or not? Yes or no? You have to apply the external force in this direction or not? See, if you don't apply force in this direction here, if you just simply leave minus q, then it is going to accelerate. Yes or no? It is going to accelerate towards what? Towards positive charge distribution. Yes or no? So if there is no external force, only force that is going to act on this one is electrical force. So the net force on this charge is not equal to 0. In this case, what will happen? If the net force is not equal to 0, then it is going to accelerate. That means its velocity is going to change. See, it is just like I have told analogy there, like if you lift up the object here, if you are lifting up the object in upward direction against the gravitational field force, what is the work done? I have explained. Similarly, I have explained whenever you are lifting down or whenever you are taking this object in downward direction, you are not leaving the object. Yes or no? So you are slowly taking that object towards what? Towards the surface of earth. So if you want to take that object towards the surface of the earth slowly, then what you have to do? You have to apply an external force in upward direction against what? Against gravitational field force. Here also you have to apply an external force. Understood? Now you can determine the work done by the external agent. Now in this case, the work done by the external agent in moving from infinity to what? Infinity to r is equal to what here? Already we have determined, that is integral r to what? Integral r to infinity. I can write it as f electrical dot what? F electrical dot dr bar. F electrical dot dr bar. Or first you can write. So first you can write here f external dot dr bar. Now here the range is from where to where here? So you are moving from infinity to r. So you have to move from infinity to r. Now here also you have to maintain what? The net force. Since the velocity is not changing, velocity is approximately equal to 0. So the net force acting on this charge must be equal to 0. So if the net force acting on this charge is equal to 0, then we know that F external must be equal to what? Minus F electrical. So that's why I have explained all these things here. Understood? Okay. So this is very important. Right. Now here also F external is acting opposite to what? Opposite to F electrical. Yes or no? So F external I can replace with minus F electrical. So minus integral infinity to r, I can write it as what? F electrical dot dr bar. Yes or no? Okay. Now if I want to make it independent of minus, that means if I take this minus sign, take off this minus sign, then I can write it as integral r to infinity f electrical dot what, f electrical dot dr bar. Understood? Okay, so this is the work done, this is the work done by the external agent in order to move from infinity to r, infinity to r. Yes or no? Okay. Okay, so now now if you consider that charge as positive here, if you consider the charge as positive, okay, so here you are having the charge distribution, let us say this is positive charge distribution. Okay, so in this case also, in order to move the charge from infinity to what, infinity to this distance r, this distance r, you have done some work. So here also we got the work done by the external agent from infinity to r is equal to what we got here, r to infinity f electrical dot what, f electrical dot dr bar. Now tell me whether this expression, this one and this one, both are same, or there is some difference between this one and this one. Tell me, is there exists any difference between this one and this one, or both are same? Tell me here. Tell me here, Venkatesh, Gopal, tell me. Tell me. See, I have already told here, I have already told that always the direction of dr bar will be taken care by what here, taken care by this integration, this integration, that is the limits of integration. Yes or no? So here dr bar is pointing from where to where, from r to infinity. So that means it is pointing from r to what, r to infinity. So that means dr bar is pointing in this direction. Yes or no? dr bar is pointing in which direction here? It is pointing from r to infinity. So that means it is pointing in this direction, r to infinity. Understood? Now here electrical field force here, electrical field force in this case, positive charge, take this positive charge distribution here. Here dr bar is pointing in which direction? It is pointing from r to infinity. So r to infinity means it is pointing in this direction, from left to right. And electrical field force is also pointing in which direction? Since here it is positive charge distribution, here you are having plus q. Yes or no? Plus q. So the electrical force is going to act in this direction. So you have to apply an external force in this direction. Understood? So electrical force is pointing in this direction from left to right, and this differential displacement is also pointing from r to infinity. That means it is also pointing in this direction. Yes or no? So f electrical and dr bar both are pointing in the same direction, and hence you are going to get, if you solve this integration also, you are going to get what? You are going to get some positive value. You are going to get some positive value. Whereas here in this case the electric force here, in this case the electric force is pointing in which direction? The electric force is pointing from infinity to what? From infinity to r. It is pointing in this direction. Yes or no? Because both are of what? Opposite polarity. The electrical force is pointing towards what? Towards the charge distribution. Understood? Okay, so that means it is pointing from, f electrical is pointing from infinity to r. In this direction it is pointing. Whereas dr bar, always you have to consider the direction of dr bar is given by what? Given by this range. So here this dr bar is pointing from where to where? From r to infinity. From r to infinity. So that means it is pointing from r to infinity. That means it is pointing in this direction. Whereas electrical force is pointing in this direction. So the displacement is in this direction. Understood? Okay. That means if you calculate the work done here in this case, what you are going to get? You are going to get negative. You are going to get here negative. Whereas here you are going to get what? You are going to get positive value. Understood? See, whether it is negative value or positive value, it all depends upon what? It all depends upon the given problem. Understood? Okay, so don't remember it as a for this one it must be positive, for this one it must be negative, like that. Understood? Just follow the procedure. So then without any confusion you can get the correct answers. Understood? Okay. Okay. Parasmoon, even though expressions are looking same, the results are going to be what? The results are going to be, here you are going to get some positive value, here you are going to get some what? Negative value. Yes or no? Understood, Parasmoon? Even though the expressions are looking same, here the electric field force is pointing from R to infinity and dr bar is also pointing from R to infinity, whereas here the electrical force is pointing from infinity to R and dr bar is pointing from R to infinity. Understood? Okay, so that means if you calculate this work done here, if you calculate the work done in order to move minus q from infinity to r, finally you are going to get what? You are going to get some negative value. Yes or no? Why here? Because this dot product is going to be negative. Whereas here you are going to get what? You are going to get some positive value. Understood? Okay. Or simply I can say whatever the results that you are going to get here and here, they must be what? They must be exactly opposite to one another. If you are getting somewhere plus, another one you have to get minus. If you are getting here plus, another one you have to get it as minus. Understood? Okay. Okay. Is it clear, Parasmoon? Yes. See, that's why here so don't worry about this positive signs, negative signs and all these things here. Okay, so just follow the concept, and apply the procedure. Understood? That is what is important, right? Okay, so the result will be automatically taken care of, okay, if you follow the concept and procedure. So whatever the concept behind this one, so if you understand these concepts clearly, then you won't do any mistake while calculating the problems, right? Okay. Okay. Shiva Prasad, hi sir, good evening. Good evening dear, good evening. Okay. So I hope up till now it is crystal clear here, right? Okay. So with this I am winding up the session for today. So tomorrow exactly at 4 p.m. we are going to start the session here. We are going to have the class exactly at 4 p.m. tomorrow also, right? Okay. So if you are having any doubts, you can ask me, otherwise we can wind it off, right? Okay. So I hope everything is crystal clear, right? So I hope everything is crystal clear. So after going home here, that means not after going home, you are already staying in home only, okay? So once we complete this session, so just revise all these things here, revise all these things and prepare a notes and try to analyze whatever I have told. Yes or no? Okay. And if you face any problem or if you are having any doubts, you can ask me in the next class, right? Okay. Okay. Shiva Prasad, when is your live class start in app, that is EMT for ECE? I don't know about that here. So still that schedule is not fixed as of now. Okay. So once I get the schedule, then I can inform that, right? So as of now I don't have any information. Okay. Okay. So they will schedule here, they will schedule maybe soon, so I don't know that. Okay. Okay. Okay, so I hope everything is crystal clear up till now. So with this I am winding up the session. So tomorrow we are going to meet exactly at 4 p.m. Exactly at 4 p.m. we will meet. So don't forget to revise each and everything. So take some half an hour or 15 minutes or 1 hour also, you can take rest. So after that at least revise whatever we have done today. Understood? Okay. Okay. So okay guys, so I hope you have enjoyed the session. So with this I am winding up the session. So tomorrow we will meet exactly at 4 p.m. So until then, take care. Bye bye.